just a warning. Okay, and we're live. Cool. Okay, so today we're continuing what we did last time, which is trying to reprove Conal's paper that is in Agda, and we're going to try to reprove it in Lean to compare the two and also to learn about writing more understandable proofs instead of just relying on tactics. Maybe we will rely on tactics. We'll see. But at least we want to learn before we just go there immediately. Yeah, and we have Jan and Paul and Conal with us today. Yeah, so just a warning to everyone, we are streaming. Just so don't talk about anything you don't want on the internet. Conal, if you are talking, I don't think we can hear you. Just
I was muted now.
Okay, cool. Just checking. Good. Oh, okay. So last time we started with like the things you see on screen. We defined a language and an empty set and universal language. But we have not defined the empty string regular expression yet. Well, we have now, but we didn't last time.
No, but we discussed what we're going to do. So I just filled it out to make sure we remembered what we were planning to do.
Yeah.
But it's not clear yet whether this is the right approach. So the issue with using the normal type class, so there's equality here in Lean, is that it's prop instead of whatever type U. So we were discussing last time whether we required our own equality, which will be incredibly inconvenient if this is necessary.
Or might be, probably will be inconvenient.
Yeah.
We're not sure yet, but
but like any, well, isn't it true that we can't use any tactics which
I don't know
involve REFL?
I don't know yet. So like,
okay,
I think we should test this theory. Hypothesis, and also, like, I think Conal answered last time. So let me try to repeat, and then you can correct me if I didn't get it right. But so the reason we don't want to be in prop and want to be in type is because with prop we say the proof is irrelevant, right? And with type we're saying the proof is kind of relevant. It represents the actual parse, which is not well, parses can be ambiguous. So if you want the actual parse that is unambiguous, then you need to be in type and not in prop. And
I would add to that, even for unambiguous languages, it's still useful to know in what way a string parses. Right? I mean, that's what every parser does. You don't just want to get your program in the language, but then you want to do something else like compile it.
Good point. I forgot about that minor detail of parsing. Okay. Now I don't think I will forget why type is important. Oh, I need some sleep at some point this week. Okay.
So
hello. Sorry.
Hi, Gregor.
Oh, Gregor is here. Gregor, just to be warned, we are streaming. Just
yeah, I know.
Okay, good.
Sorry for being late.
No
problem.
So your inductive equality definition there looks like it has 3 alpha arguments instead of just 2.
I'm not claiming that this is correct.
No.
Okay.
It only has 2 alpha arguments.
Yeah, this is just to define the alpha.
Yeah,
so I guess we could actually omit. We could actually omit this, I think, maybe.
Oh yeah,
Yeah.
of course. I got it. Yeah, Agda's the same. I would misparse.
Yeah, but
I'm
in
not
this
sure
case,
about this U, but
No,
where,
no,
where
no.
does this U come from now?
I think maybe keep the use there because we have somewhere a U+1. Like
Exactly.
let's keep it there for our sanity.
Yeah. Because I'm not sure whether this U should be U+1 or whatever. I don't know. I imagine I think it's U, but
this
Yeah,
way we
it's
can
probably
figure out and
low
not
as you can get
be
away.
surprised.
yeah.
Hey, Paul, can you move stuff to the left of the column? Because I think you need to give a name to the alpha.
That is
Oh,
So can you bring
need
up
to-
the Agda definition on screen?
sure. Got it here. This one.
Yeah. You have this X colon A that's on the left
Yeah.
of the semicolon, and that's relevant.
Okay.
yes.
Hmm.
It's X equals X. Oh, A. Oh, I see. So that A
So
is
we've got
X.
an A.
Mm-hmm.
So that's my.
Oh, that's
No, but that's my universe level,
Yes, correct.
and this is my type,
It's
Mhm.
your
my X.
Yes.
Oh, yes. Yeah. This is nonsense. Okay.
well, not nonsense, but like just
So what do I?
yeah.
yeah. That,
So
That's the colon.
exactly.
Yeah.
And then
That goes away.
you remove this.
Yeah.
Exactly. And then XX.
Yeah.
X.
Yeah.
Okay. Great. So then, is this definition correct then?
WE looks like it to me.
Yeah. Yeah.
Okay.
So now maybe, yeah, we should try to prove Rick. No, maybe it's too early to see if a tactic would work. Maybe we continue first with defining more operators and then.
Sure.
Yeah.
So let's should we go back here? And so this one, and
This is the character.
this is the character one.
Yeah. So it defines that, yeah, we're taking some alpha as input here.
Yes. So A. Oops.
Yeah.
Or is it this?
Yep.
Okay. Then we have this is.
So this is like a helper internal operator, right? This is not a real regex operator. It's gonna use later to just get rid of a lot of if and else's that you would normally.
Right.
And also to extend from recognition to parsing.
Oh.
So for recognition, it's a if then else, and then Berezovsky had a little trick.
Yes.
Yeah, for that. But I had to change that. That was the one rule I had to change in Berezovsky's in order to get parsing instead of recognition. And this operator was the key to defining correct parsing on I guess it was concatenation.
Okay, so this is more than a trick. It is an internal operator, but it is more than a trick.
Yeah.
Yeah. Okay.
And it also, if you think of languages in terms of like vector spaces or modules, like most of a vector space structure, then this is scalar multiplication in that space. Turns out to be the thing you need to do to extend Berezovsky's method from recognition to parsing. So that's just a little tease.
Wow.
We'll see when at concatenation.
So what would we call this operator? Because we like
call
to name things.
Oh, I call it scaling,
Cool.
but I think of it in that abstract way.
Yeah,
Yeah.
that's fine. It works.
Okay, so what's the
So S is a proposition and P is a
Mhm.
language. So
Okay.
if you think of it as Boolean, right? Then when S is false, you get the empty language, and when it's true, you get the language P. And so that in Berzazowski called that lowercase delta. I think that was his lowercase delta. It gave you either the language containing only the empty string, or it gave you the empty language. And then if you concatenate that with something else, you either annihilate it or leave it unchanged. It's like it's a 0 or 1 is what it is. It's the 0 and multiplier. But if you want proofs, then S is a proposition. Well, S is a proposition. And so all the different ways of proving S come into play here.
But our propositions are types. So S is just a type.
Exactly. Yeah.
So you could imagine that S is just the what did we have for S could just be unit or empty, for example.
Exactly. And in that case, this operator is just like Berzazowski's lowercase delta, the thing that gives you the empty language or the language containing only the empty string. Yeah. And that's 0 or 1. In other words, if you concatenate that with another language, you either destroy it or leave it intact, unchanged.
I think I can just translate that to something I've had before here. So like basically like the nullable function can return true or false in the Boolean things, right? But then Berzazowski does this little trick where he doesn't return that, he returns empty set or empty string. So then when you write concat, the rules for concat into the derivative, you can rather call this weird nullable function instead of using an if else. But like, so maybe before we get there, let's just define this operator, and like it will be so clear when we get to defining derivatives. So I think it's best to just define and ignore for now.
Me too.
Like,
Okay.
yeah, like when we get to derivatives, you'll be like, this thing.
Yeah. I was going to need this operation either until I figured out concatenation with proofs.
Yeah. It's only necessary. Yeah. When you get to concatenation is the only place we will get to understand it.
Yeah. So yeah, it's fine if just skip it for now.
Yeah, or just define it like, but don't understand that it is not understandable right now. Like, so I just like call it scalar.
A scalar, okay. And then this is a
the first
alpha.
one is a type.
Right.
So
Alpha type. Oops. And I've got a language.
Yes.
Let's see.
Yes.
And then we have this. And then we had a product.
Yeah, so so product is the propositional and, but we don't have that in types. Well, we have tuples, right? So I guess this is a tuple.
Yeah, it's a binary type product.
Okay. So the tuple of
a alpha.
Yes.
Yeah, maybe we should call it S for scalar. Like,
sure.
It might be the more.
Yeah.
Yeah.
We're breaking lean conventions here.
Yeah. Yeah, but in this case, it is like.
Oops.
Yeah, and just the fun there.
Yeah.
So
then we have failed to infer. Make this bigger.
Okay, there's some space there.
Oh, right. This isn't the pair of S and P of W. It's the product of S and
Oh, it's
P
the
of
product.
W.
It's the type.
Yeah, it's the type. Exactly.
Yeah.
Okay, so now we have universe issue.
Cool.
Oh, do you?
Nice.
No, do we? I thought we.
Yes, type U1.
don't know how to synthesize the implicit argument. What's the implicit argument here?
Takes a W.
That should be the universe level, probably. So P has one implicit argument, right?
Yes, yes, yes. Okay, so I need to, can I give it that? Oops. No. How do I pass it? Because lang is this thing here, so it has this
I think you
implicit
use an
argument.
at. I think you use an at somewhere.
Okay, maybe.
On P, like
Yeah,
at
I'm not
P.
familiar with this.
I think at P space U.
So that tells it to go into implicit mode.
Yeah.
Maybe
Okay.
this. But I need to actually put it here.
Yeah. Yeah. U universe.
No, it's bound here. Look.
Yeah.
U is bound.
Mm-hmm.
So it's bound for this guy, but it's not in the.
Yeah.
It's bound in the type, but not in the.
Yeah. So we're gonna add an implicit U.
Maybe between fun and W.
Yes, there we go. It's happy.
Oh, there.
Okay.
Yeah. So yeah, maybe just name U. I guess we don't have to name it. Maybe it's but
Just out of curiosity, would it also work if we wrote the return type of the function?
Right. Okay.
This should
This.
be lang.
Lang, yes. And then. If I just get rid of the. Will this understand what we're. Oh, there we go.
Oh, better.
So why did you expect that, Jan? That's interesting.
That's some good type inference. Well done.
Yeah, well, I mean, usually with universes, if you write the types, it's smart enough.
Right.
Cool.
So if I hover over here, there's some U that's hanging out here. And so it's put the U in here. Okay. Somehow it knows it's somehow related with this U.
Yeah, well, they're both lang, so maybe, yeah, they just connect there.
Okay.
Okay.
Well,
so
we learned how to
worry about
we learned
this.
how to apply implicits.
Yeah. But don't worry about what scalar means right now. Let's just, yeah, we have it ready for when we need to understand it. So we can go to or.
This is or. Yes.
So just one clarification. I think that the lang in the return type is applied to U+1.
Right.
But it's hidden, so it looks like the same type, but they are not.
Oh, okay.
It's telling me if I hover here, it's saying type U+1.
Yeah.
And here it's type
Same.
Oh no. Oh, maybe I'm wrong then. Could we try? Can we try it just to be sure?
It has to be the same. Otherwise, we're gonna like just.
Climb up an infinite ladder.
Yeah. Yeah. I would be very afraid if it's not the same.
How could we check that?
So with at, and then you provide an explicit U.
Oh, I see what you mean. So if I just put this here, it's going to fail. So I need to say U+1.
No.
No.
No, so here it would be U, and then in the return type, you try U as well and see what happens. And I guess you need to bind the U, maybe. That's expected.
Function expected at term has type U232 + 1.
Yeah.
Maybe I don't know. Maybe I need more parentheses.
Is
No.
that aces u, right? I'm wondering about aces u. Like, I feel like that might need to be like u minus 1.
Oh, because the implicit argument in lang is a type, not a universe.
Oh, yes, sorry. Yeah.
Oh, okay, no, I got it wrong.
Well, well.
Oh, I don't know how I.
But how do you provide this u then in lang? Is there like?
Is there an implicit? I was expecting
is-
there's some implicit here because I can do this.
Yes.
But it doesn't. This doesn't work.
No,
On
Can
the
you-
universe level.
so it's just
Oh, sorry.
lang is a type and it's first.
Yeah, my bad.
Oh no, okay.
But this here has to be bound. Has to be come from somewhere.
Yeah, hover over lang.
Yeah, what could it give us? Oh, it's got some associated. Look, it's got a dot universe. So there's some universe associated with this thing.
Yeah, so maybe you can apply it like that with the dot instead of the at.
Right.
Does Lean have module parameters?
Is a
That
Coq
you
has
could
lots
give-
of module stuff, but
Yeah.
Lean has less of it.
Oh, this somehow
You might
does
also-
something.
and also the alpha type be module parameters. Then they would never need to be inferred.
Yeah, there is. I think you can
Or
say at the top you can say universe u, and then every function is in that universe.
Oh, yeah, no, I
Yeah.
meant something more general. Can you give
Yeah.
types and value proofs and all kinds of stuff as arguments to modules?
This,
I don't
yeah,
know
this
if
this is very popular in Coq.
Okay.
Yeah, but I never liked it. So when I read that part of Lean, I skimmed over it.
Oh, but it's
That's a-
usable. It's usable in Agda. In Coq, it's
Yeah.
not usable.
I just looked up how to provide the U. So what you do is you write def, and then you would write def lang dot, and then in curly braces U.
Oh, so you can bind it here. That's how you
Yes,
bind
yeah,
it. Okay. Yeah, somehow this syntax means something as well. If you provide.
But is this
Interesting.
different than adding like an implicit regular argument before type? Is this only syntax sugar for that, or does it have a different meaning?
Yeah, I don't know where the U comes from if you don't provide it, because in
I can do
the
this doesn't let me do this here.
Well, but U colon level and then or universe. I'm not sure, and then an arrow.
Universe. Small u. Universe.
And then an arrow after this. Yeah.
Okay.
Yeah, you need it. Yeah.
well, in the
I don't
in
know.
the Lean tutorial, it says you can provide the universe with universe U. So you just write universe U before the definition. It doesn't seem to be a type in that sense.
Okay, so I can write it.
No.
So
it is.
that's different than in Agda then, because if you do this, it says U it's unused, but that's how
Yes.
you do it in Agda usually. So that's okay. Then
That's interesting.
it must be doing something else. Yeah.
Yeah, this is also how I know it from Agda, but in Lean it seems to be like something more general, or I don't know. So it has a special syntax, which is just writing universe U before the definition, and then it is you declare it that variable
then if-
globally.
So before the definition, you mean before this colon or before the assignment?
Before the line, in the line before.
Oh,
Yeah.
interesting. So I write universe.
Yeah,
U?
but then it's file level. Then it's not like just for that definition.
Oh, it's file level.
That's-
Okay.
Yes. Yeah.
That's not what I want. like then it's yeah. I don't know.
Another option is not to generalize over universe levels or even over the element types, just to wire them in for now, and then understand it, and then decide if you want to generalize it if you like it.
Mhm.
That way, you would be, getting more
Yeah.
focus on the language stuff and less on the lean details. But that's up to you.
Yeah. Yeah, I also feel I've had enough of universes for now. Like this is
Well, I mean, the thing is, it's sort of. It looks like it's working here.
yeah,
I don't know.
Yeah.
So
Yeah.
yeah, exactly.
maybe we
This
don't
is
need to
good
worry
enough.
about them.
Yeah.
So what we got? Or
Yes.
Hmm.
I don't know if I
We're-
can use.
We're taking 2 langs.
Yeah. What did Conal call them? P and Q. Good. So-
Yeah.
Okay, I'll give it the type this time. This is a product. Oh no, disjoint union. Okay.
Yeah, so this is the either. So I think we have some somewhere.
Right. So
What
this
is
is actually called sum.
Yeah, what is it called? Hopefully some. Yeah, capital S sum. Actually, even
Right.
think like the /plus might work, but no,
Oh god.
that's wrong. No, that's definitely not it. It's a different
Maybe.
symbol. I have it
Well, we can
somewhere.
maybe look up in the. Maybe it gives us the.
No,
Oh, it's
I'll
not
go
going.
find it.
Ah, maybe I need to import something actually. And it's not going to like this or because it's we need to give it some other name, but right, great. So this is the right thing. The disjoint union. Okay, so I can O plus. How do we feel about Unicode?
Yeah, we're happy. We're happy.
Should we try? No. Oh, I'm terrible at writing. No.
There we go.
Okay. Right. This is a. Okay.
We didn't make that one up. It's yeah.
Yes. Great.
We're supposed to know it.
Yeah. So then we've got. What would it be? Yes.
Yeah.
And this is the product.
Yeah. Yep.
Great. Great.
Yeah, concat. So
Concat.
yeah, we need a exists here.
Mhm. So this one is exists. Magic exists. Some exists with.
That little magic
Ah.
exists. Oh, there we go. There's the explanation.
It's just
Doesn't
exists.
like, can't sort out how A, B, B should depend on A, B, A.
The point is we're quantifying over two strings. So
Oh, yeah. I
Different
think
ways to
Lean will do this for us. Let's hope.
yeah.
Right, so
I think it's
So how do you say that?
backslash.
Just a
exist.
U and a V.
so we need two
to
U and V.
yeah.
Oh,
Yeah, you don't. I don't think you need a
oh, sorry, yeah, not
comma,
pair.
maybe.
It's just this thing. Yeah, how do I do this?
Ah, good.
Explicit binders. Yes, there's only one.
There's commas. You can put commas between. Yeah. Sorry.
Yeah, commas. But I think I put parens, which was wrong.
Yeah, but you need. I think you do need the type maybe. So we just need to say list of alpha maybe.
Mm-hmm.
Is it another comma?
Yeah. I need to look. I just need to look it up.
Yeah. I will say.
Existential. Okay. So we do exists and then comma. Sorry. Yeah. It's not happy with this, so we're doing something wrong.
Okay, just do the U for now,
Yeah.
and then let's just get the syntax right.
Yeah.
For the both. So W equals U plus U.
Yeah. Okay, so we need to bind this somewhere. Great.
That's fair.
Oh, yeah. Right.
Maybe new line. Maybe.
Yeah, we can new line.
It's the suggestion.
Right. Oh, we can't use equal.
No.
We need to use. Oh,
I think this is a normal equal. Yeah. No.
oh, sorry. Yes.
Yeah. I think this is a prop.
Because these are.
We can check the Agda.
Sure.
Yeah, maybe.
Oh, it's not. Oh, okay.
Except that
It is a triple equal. Okay.
yeah, but if this equality is proof irrelevant, right, then maybe it doesn't matter which version you use. You can use your prop equal. I bet you can use your prop equal. I'm not sure.
No, we are taking a product.
Yeah. You
I
type,
don't
yeah.
think we
So,
can.
yeah, you're right.
We need to do
Rick.
relevant equal.
Yeah.
And then we.
Cross. Oh, also, why can't we do plus?
Happy. Well, so this. Sorry, I've lost myself. Yeah.
PU and cross with QU.
Yeah. Thanks.
Okay, so
then we can look and see what's wrong here. Oh dear. Out parameter. This is new to me.
What? What's that?
Oh, there must be something related to the existential. That's not helpful. Let's go back to the documentation.
Also, maybe it's a sigma and not a exists.
Oh, okay. Cool.
Just
yeah. Let's. So, did it have it here? The sigma.
I had it in the other page you opened.
Oh, sure. Yeah. The documentation.
I was
this one here.
Yeah, that one.
This is not useful when you jump to this because this is not what you want to see. This, right? Okay, so let me see. The exists is going to be a prop. Yes.
Hmm.
So we need the sigma for the type.
Yeah.
Let's just hope that works.
Yeah.
If not, we'll come.
That's just my first case or third case.
So sigma. Ah, okay. So everything is wrong now.
Okay, but this is better.
Okay, stuck solving some constraints.
Yeah.
Is this better?
Yeah.
Okay.
I don't know why, but
Oh no, we've got universe problems.
yes. So okay, this is
Yeah.
this is better. So
Yeah. Oh,
so
I'm using U for universe. This
yeah,
is
no.
confusing.
But like I know what the problem is. So like alpha U, right? If we look at Lang on line 3, you can actually see
Yes.
alpha U is Lang. Like Lang is U plus 1. Alpha is just U, right?
Mm-hmm.
So we need alpha in line 22 to be U minus 1. Like I don't know if I don't think you can type that, but like we need to make it clear that Lang is in U plus 1. So maybe
Well, hopefully I can do this trick,
yes, I'm hoping you can do that. Yeah, that's
and then I shouldn't shadow the U in the definition.
yeah. That's
not shadow the
actually
U.
very important.
Yeah.
I didn't see that one.
Shadow the U, so we need to. I don't know. V.
X.
Okay, X is good.
X comes after W, right? W, yeah.
Okay, so we still have issues, but
The
okay,
final Lang also needs to be U plus 1, the return. It's probably inferred, but let's just make sure. Okay.
all right. So why is this one PX happy, this one not happy? This is very confusing.
X plus plus. What is this one's problem? Oh, okay. Let's remove the plus plus for now. Like, what happens if W is just equal to X?
Sure.
Okay, interesting. So we already have an issue here.
It's a universe level.
So
I wonder if it's your product type constructor, whether your product type constructor requires its arguments to have the same universe level, or whether it takes the max of them as it does an egg.
there was some max. I saw a max somewhere. Yes.
Yeah, there was max in there.
But they everything in the product does have the same universe level.
Does it? Okay. Well, then never mind.
That's why. Am I wrong when I say that? Because
I don't think so. I think you're right.
Maybe I've got to do something. I'm getting confused with these X's. There's an X here, and then
what we can do? There's another type we can add for W. We can add another type.
So W's
list of alpha as well.
Yes. Okay, so we've actually got the genuine. Okay.
That's list type.
So there are different alphas going on. Look.
Okay.
There's an alpha and alpha Christian crucifix.
Yeah, that's not correct.
Following variables have been introduced by implicit lambda feature. Wow, this is not an implicit lambda, is it? It's an explicit lambda. You could disable implicit lambdas using @ or writing a lambda expression with something or something notations. We should do that. So where do I put my @ symbol?
That's
let's look up explicit lambdas.
I've not seen
Oops, this
I've not seen one yet.
control panel is in the way. How do I move it? There we go. So you can't see that, but my Zoom control panel's in the way. Whoops. Okay, so that's the wrong name, perhaps. Maybe I'll search for implicit lambdas and it will tell me.
Yeah, I did. So you put you put an at in front of the fun.
Okay. And that turns it into an explicit lambda.
Yes. So now you have to.
Does that mean we have to put the alpha here?
Yeah. Yeah.
Okay. And then I have to put u.
Yeah.
Oh, but
We already have.
whoops. It has type. Okay, so we just lang of type u+2, because
maybe
So,
I did.
this u and this u are the same, but here they're different or something.
the alpha in the type, do we need that there? I don't think so.
This alpha here.
No, the one in the line 22.
Yeah, that's
Oh.
also.
Okay. Yeah. So I was trying to. Okay. Alpha type, list of alpha type u+1 to type u+2. Yeah, this doesn't match this thing, does it? So we have an extra argument.
Yeah.
Where is the extra argument? I cannot see it now.
So there's, it's saying this type here,
Mhm.
and I have 1, 2, 3 arguments, and it's expected to have type lang, which has.
Right.
No, but is that right?
Okay. So I think we do need that alpha on line 22. Sorry, like we can delete it in a second if I'm wrong.
Yeah.
On line 23, delete that. Yeah.
Yes.
And just write alpha.
So it's that alpha we want.
Like that. There we go.
Okay.
Nice.
Okay, wait,
Oh,
but
but
I'm
now this is not used. Now
That's
we can.
not you. Okay, delete that. I was wrong about that.
What is this? Where does this alpha come from then?
There we go. That's that easy.
it's being bound here.
That's.
Oh, so I could, instead of this, I could write alpha type, but then the type level was wrong or something.
Yeah, do that.
Let's just check, because that's mysterious. Okay.
Ooh.
So we almost got it right. We just got the wrong universe level. But
Okay.
the error message was, I misinterpreted.
But can we delete all the U+1s? No.
Yeah, that's.
Maybe I was wrong about that.
No. Well, it's got us further along the road, so we could see the actual error message. Well, it's already
I hope I
happening.
was wrong about this. I really hope so.
Oh no!
No. Delete the last one as well. No, you were there. Delete the alpha one as well.
Delete the alpha?
Yeah.
So it can infer the whole thing.
Yeah.
Just alpha.
Yeah. Or just alpha type U if you want. Like either way.
Well, this has no universes anywhere, so I'm happy to delegate universe bookkeeping to the compiler.
Yeah, exactly. We shouldn't be doing this. Like, okay.
Yeah.
Right.
Okay, so we can. This is, so we've learned. So would this work? No, this would not work.
Interesting.
And then if you write the alpha in braces.
Yeah, so I don't think this is
that's a good idea. That's a good idea. Yes. There we go. Nice.
So how many different syntaxes are there for doing
For
implicit applications?
A lot.
Yeah. This is
it's
not
important.
nice. This is if we can use this form, I'll be happy.
Yeah.
Okay. Now we need to do that. We haven't defined. We haven't. We still need 2 arguments here.
Yeah. But it's
You can
first-
write a nested exist in the or sigma, right?
Yeah. But this looks like we can have multiple binders.
It does look that way.
Explicit binders, PP space bracketed explicit binders, or unbracketed binders, explicit binders, which are, we do,
colon term, comma, colon term. Like, do you do like X colon list alpha, comma, Y colon list alpha? That would be weird, but yeah, definitely.
no, surely not.
No, like X colon list alpha.
X colon.
And-
The type.
And then, yeah.
And then the
comma Y comma Y colon list alpha, and then yeah. Oh, interesting.
No.
Still not okay.
So we should be able to do it because we just can't
Yes.
figure
Yeah.
out what this is telling us. Whoops. Bracketed explicit binders. It's a bracket. Oh wait, there's no comma.
Okay.
Perhaps we have to read we have to read the parser, which is kind of
I would be
a little bit ironic. There we go. Yeah, we just have to read the parser.
nice.
As long as you can read the parser, you're fine.
Yeah.
Will this work?
Oh, yay. There we go.
Phew.
Beautiful.
Okay.
Ish.
I think Agda's already winning on the beauty contest.
Is it okay?
We'll see.
Yeah.
Yeah. I'm not calling it yet.
Yeah.
Okay.
Well, and
Good.
I massage my Agda code a lot to make it beautiful. So
Yeah.
you
This
get
is
to
the
do
first
that.
time. Yes.
We've got star. Are we calling it star next?
Yes, please. Like,
Okay.
there is no better name for this.
Well,
Zero
unless you
or
use a
more.
Unicode star.
0 or more is horrible to write.
Right. Shall I try and get away with that with the type inference? Okay.
Yeah, you could try. So yeah,
We've
basically
got-
there's a list of alphas.
I do. What's it? Yeah,
The
there exists
W's.
list alphas.
Yeah.
Such that equal. Then we need this thing all. Oh, it already needs this. Yeah. Oops.
Let's hope we have.
Do we have concat for lists?
We have it somewhere. Like maybe. Okay, I'll go find it.
And something else. But this all.
Yeah.
Oops. Okay, so we have pred here. So is this like prop? No. Oh no, predicate. Sorry. Yes. This is in unary relations. I'm hoping we have. Well, something similar in Lean will be the wrong thing.
So just the concat is list.concat. So
Thank you. We may need to
should be.
No, I think I need to just give the types because it's complaining about universes again.
Oh, okay, great. Okay.
So let's.
I think it was complaining about the arity of the function.
Oh,
So is concat for two lists or for a list of lists?
yeah, it's for look. L.concat A appends A to the end of L, so it's L plus singleton A. So it's like it's like a flattened function or something like this.
Okay. Okay. I'll go. It should be there. Don't worry. They're working on a better way to. Well, maybe they've already done it now. Let me actually check. They might have finally upgraded the standard library hosting. They did. Still doesn't make it easy to find what I'm looking for. Ooh.
Yeah, this is not easy.
We don't have a Google.
I saw. Well, you're pointing me to Lugal. There's Lugal, isn't there? But
oh yes, I forgot.
you told me about this Lugal. I don't know how well it works. So I hope this may work like Google. I don't know if you can say like list of A. I don't know who's paying. I don't know who's paying for this, so I feel bad.
No. I think the foundation is
Okay. Yeah, so
not-
maybe
not very helpful.
maybe if he just gives me all the stuff about lists. I mean, it's.
Isn't it join? Isn't join the word that people usually use?
It could be the join. Let's. Aha! Indeed. Look, Lugal found it.
Okay.
Right.
Only
Well, it's easy if you know that if you can guess the name.
Yes.
Then this is useful. Because this is better than searching the source code.
Yeah.
Great. That is actually useful.
I hope so.
What? Yeah.
I'm not convinced yet, but I'm definitely trying it again.
Oh, but there's also we should. There's also this, isn't there? These pragmas.
Maybe find question mark.
Yeah, there's something like this you can do, where you can search for stuff. But I don't remember it now.
Yeah.
Okay, so we're
but
not
we
using
need-
the P here, which is bad. Oh, yes. Because we need to actually do
Yeah, because we still need.
Right, so maybe there's some all here. Remove all.
I think. Well,
There we are. But this is bool.
yeah, no.
Yeah, this is not good. So it's actually nothing to do with list, is it? It's
Yeah.
we can try if there's this some all thing.
I think we just need to define our own. But It's not for now, at least, because it's not it's not that complicated. Something like a list thing for me.
Mm-hmm.
I think the sorry, just trying to find it.
Okay. So we have we need some predicates.
I think it's like, oh yeah, there's an, yeah, we could just copy that. Great.
So what is this symbol?
That's the least upper bound. That's the max.
Oh, the least upper bound. Ah, okay.
Do we need that in this case? Is it maybe that's just for the very, very general case?
I think we never have to think about this before because we were always in prop, like with the stuff we did before. So now this all becomes important. When we were doing the stuff before, this was never important.
But this is, I think, only important if there is if you are for alling multiple user type levels, but will only be for alling one type level, just like as if we were in prop. So
all right, so maybe we can get away.
I'm hoping we can get away with it. Yeah, like
okay.
Yeah, I might be wrong, but like,
you want a P? So what's the type of my P? It goes from
it's just type U.
Uh-huh.
Oh yeah,
It's
something that takes
it takes an alpha,
yeah.
right? Type.
Yeah, it's an alpha
Yeah,
that gives
sorry.
you type. And yeah, that you might need to be different from the other one.
Right.
Yeah.
Well,
that was my U and L, I think, or A
Right.
and L or whatever it was.
then we have our
No. Maybe copy
No.
that line from Agda. You have to
Sure.
switch
yeah. My screen is not big enough.
those three lines. Yeah.
Oh no, they're not. I'm not in. Can't do
You're
that.
not something that
Yanking
allows
up.
you to use the mouse.
Yeah.
Okay. Like, okay. Controversial.
P. Sorry.
Yeah,
the
I need
second
the
alpha
third
we're
line
missing.
as well.
Third line.
The top line. Can we maybe copy the top line as well?
Oh yeah. So I'm missing the list, of course.
Yeah, because we're gonna go back and forth
Sorry.
there a few times, right?
Yeah.
And,
There's
yeah,
no list here.
Just comment it out, like, so
Yeah.
we just have this reference.
Yeah, so we've got a predicate. So the
Yeah, and
what I do to, and then this on the right hand side is list A, and then oh sorry,
yeah,
a predicate on.
don't
I'm writing in the wrong place.
Yeah.
So we get something list alpha to type U.
Yeah.
And then my constructors need to. Sorry, yeah.
Yeah, maybe you also want to copy those two lines into comments, just.
Sure.
I'm just 99% sure we're gonna make a mistake. Yeah, so I think maybe you can just write all P empty. Yeah.
Yeah. And then this is a function.
Yeah. For all. I think maybe you can almost actually copy that line of Agda. It might work.
Oops.
Just
What I
yeah.
wanted to
Just
do.
put,
I wanted to copy the end of the line, but that doesn't.
Yeah.
That binding doesn't seem to work.
oh.
Apart from the Unicode.
It's like
No,
yeah, we also
it's
support
not
that
quite.
line. Oh, so
But
close.
that needs to be.
Oh, colon? No.
Yes. Okay. And then this is the list cons.
Ding. No. No, we also do
Double.
double.
Oops, no comment.
I think
I
you
don't
should have the
understand why.
arrow. You should have the arrow before this.
Yeah.
So is this for all syntax allowed in Lean? So just after the colon for cons, you have for all. Is this allowed in Lean?
Yeah.
Okay, I didn't
Should-
know.
Maybe comma instead of arrow. Maybe comma. Yeah.
So it's
Right,
like in
okay.
Cork, right?
Yeah. Oh,
Interesting that these are not. We can put these on the right. So why are they named?
This is so Agda suggests better names when you refine stuff.
Right, so we don't have that. We don't appear to have that.
well, you can use
facility.
you can use underscore px and name. Yeah.
Okay. Great.
Cool. And now we'll have some universe issue when we try to use this, but
Yeah. All in. Was it P and then the WS?
no, it just works.
Don't criticize it. The compiler's happy.
Okay.
Suspicious.
Very
As it crashed, I think it was the compiler.
oh, there still seems to be fine. Okay.
Yeah, look at it. All right, so we came out of that one unscathed.
Oh, that's good.
Right.
Maybe a 5-minute break,
Oh yeah. Yes, please. Just.
and then we take on the next part. Like,
Yep.
cool.
Thank you. See you in 5.
See you in 5.
See you in 5 minutes.
Excuse me.
Well, I have an idea. We just defined these from Agda into Lean. We can also see how similar it is to what we defined in Coq 3 years ago, I guess. I don't know when, 2 years ago.
Yeah.
Because there is definitely similarities. I will send the link on the Twitch and Zoom chat, and it's convenient for everyone.
Right. Lang is string to prop.
This is what we had before. Yes.
Yes.
That's a good start.
Yeah. Like we proved that it was decidable, which took very long.
Oh.
But yeah, we had a lot to learn at this stage. So okay, if you go to the top, like this maybe.
Sorry. Yeah.
Yeah, but when I opened this file, I also just scrolled through it because I was like, "What's going on?" But like, I now get it, so I can take you through it. So online, so okay, just for Gregor and Jan, like this is the Coq we defined like 2 years ago. That's also defines these regular expression operators, but here we define it in prop in Coq, and in prop, not in type.
Yeah.
So we have on line 16, we have language, which is our string to prop. And our string is defined on line 14, which is a list of alphabet. And alphabet, for some reasons, Coq doesn't have a good string library. So we, or didn't at the time, it might now. So this is just, I think, 0 and 1.
Yeah. So it was just, could be any disjoint set.
But it was important that it is decidable. That was important. The rest was we would be able to change. So elem is this function that just applies the string to the prop. So it's just the predicate basically. So that, and we only have this function so we can write in, so that on line 20 that says like the string is in this prop. So then if we go to, scroll a bit down to 44. Yeah, this is good. So here we have the inductive type for the empty set, which has no constructors, right? So it is basically the same as doing empty or false.
Yeah.
And if we look at our lean, if we go back, and we can see, scroll up a bit. Yeah, there's our empty set, and it's empty, and empty is an inductive type with no constructors. Okay, back to the Coq. And then on line 58, see our empty string. So this is a bit, so this is why the comments are there from line 61 to 69. You can see it's basically saying for all string, because language, remember, lang is a function from string to prop. So it's basically saying for all string, s is equal to the empty string. Which is, it's the same, but it doesn't read as nice. Yeah, so already, but yeah, you have to pass in a string, and that string you can pass in can only be the empty string. Otherwise, you cannot construct the empty string. That's
okay.
way of looking at it. So if we go back to the lean, because like effectively that's what's happening on line 18, because we would need to provide a proof that W is the empty string.
Yeah.
But in Coq, we're saying you need to provide us the string, and that string you can provide can only be the empty string. So it's after many redefinitions, we started out with something like this, like there has to be an equal, but we moved to like just this is the only way you can construct it, because then yeah, some proofs became easier, but I can't remember.
No, I don't remember why.
Exact.
Just we didn't start out with this approach. Yes.
No.
Yeah.
This was the 5th iteration or 6th.
Yeah.
And then you can see the symbol. So here again, you can see like our 3rd parameter basically becomes our reflexivity. There's a word, constructor. I don't know. Yeah, not that's not the word, but yeah. And if you go down, we'll see or. This is exactly what we did now.
Yeah.
Okay.
Right.
This is the predicate P of S, Q of S.
Yeah.
So you're defining kind of things at the inductively at the predicate / language level instead of building them out of simpler things. But like so I built or out of disjoint sum out of sum, right? Rather than making a new one. So
Yes.
in other words, sum is inductive type. So rather than making a new inductive type, I use that one.
Yes.
Yeah.
And I think the same is true with equality. Equality is an inductive type, and you made more such things for like the empty string, or you could have used the one inductive type equality. They both work.
Yeah. We created new constructors, and you use definitions to reuse existing constructors. Yeah.
Yeah.
Good point. Yeah.
So it's kind of a software engineering thing. It's not a big deal theoretically.
Well, we'll see.
Yeah.
Yeah, theoretically it's the same, but like, yeah, the proof engineering has a big effect on the proof engineering.
That's right. Yeah. Because there's tons of already proved theorems about the built-in thing. So reusing them,
yes,
we get to reuse them.
Yeah.
Okay,
and then we also add not, which is
nice.
Yeah.
Okay.
That was important to me. So not in, maybe we can scroll up to not in just.
Yeah, so not in was.
Oh yeah, not, which is just implies false, right? So this would be imply empty.
Yeah.
Yeah. Okay. Then, yeah, we had concat. This kind of is the same. So yeah, here we have 2 definitions of concat.
Oh, sure.
And oh no, sorry. No, this is just
we've got star. Yeah.
There's another file with 4 definitions of concat we've proven are equivalent.
Yeah, it's this one, isn't it? Concat lang.
Yeah, concat lang. Oh.
Yeah, so it uses exists instead.
Oh. Yeah, so this is
so
the one.
This is more like
finally.
we have now, yes.
Yeah.
And then we show that concat x, concat lang x, concat lang are equivalent.
So if you go back to the lang, then we can see what concat lang looks like. Because it's not using it and exists. Yeah.
Yeah, so for all. So you provide the equality, sort of.
Yeah. So instead of using exists, we force you to provide all the parameters. So
they exist by the virtue of they've been passed into the function.
Yes.
I don't know how to express that. Yes.
I know. I think that says it well. Like that's yeah. So when you prove things, when you have something concatenated, you have to provide these proofs. It makes proving things one way easier and proving things the other way harder. And so it's actually useful to be able to switch between the two definitions. Yeah. And then again, Starlang, here is just one thing is different, except for the for all instead of the exists. Because you can see here we've unrolled the all into Starlang with the empty list and stuff. But there's on 128, there's the interesting part, which is that we assert that the first string is not empty.
Whoa.
Yeah. And this does help with unrolling the string for proofs, because it takes away one of like this bit of infinity that can happen. That you can just say, oh, Starlang is just two strings concatenated with each other, where the first is the empty string. Okay, let's go to the next constructor of for all. Okay, so the first string is again the empty string. The first string is again the empty string. The first string is again, like, you don't, yeah, you can get rid of this because you can say, I do support the empty string because of make star 0, right? So there only needs, like, the first string never needs to be empty again. Just like with a cons.
Or recognition.
Yeah.
Parsing it does. Yeah.
For parsing it
Parsing.
does, yes.
Recognition, parsing.
But also,
And also
would you want those parses? Like, so these make fewer parses possible, right? And it makes also sure that, I think it makes sure that, I don't know if it makes sure that they're not infinite.
Why would you want to?
I don't know. Just for not having an infinite parse forest might be nice. Versus practically speaking.
Yeah, I mean it's funny because you change the semantics, but it's kind of for almost an operational reason. Right? It's like your arguments aren't about what's true, right? It's sort of what you anticipate to be convenient about dealing with the results or something like that.
Yeah.
Yeah. So, and also your argument about about how is this sort of probably correct while having this requirement that P is not empty.
Oh no,
is,
we've proven that.
Yeah.
There's a proof. There's a Starlang file.
Oh, okay, so you have two different Starlang definitions. Oh, okay.
Yeah. Let's check that I'm not.
Let's just maybe check we didn't abort it or something.
Yeah, we have. Oh, this is the one that we have multiple. We have 3.
Yeah.
Yeah. There's one that doesn't.
Yeah.
Oh no.
75. Yeah.
Yes.
Yeah.
Yeah. So Starlang empty can include P is empty. That's why it's the weird name. Yeah. And this one is exactly like the one we have in Agda and Lean, except for the exists. And I think if you scroll up, maybe
you could argue that it is, right? But it's like you might be arguing fallaciously, and I might fall for it. In other words, like the fact that your specification here is tricky. Right? Your specification is clever. In other words, it's like compare with the one I wrote, which is with the concats, right? Existing concats that it reads, right?
Well, 75 to 82 is what you defined. It's just very verbose.
Yeah, if you inline some things, right? If you inline and mix it together. Yeah, exactly. Yeah. So, but this is like reading do, and I need to check, you know, if I'm reading your work,
Mm,
I need to check using my head, right, that you inline correctly. And if you didn't inline correctly and I don't catch your mistake, then I'm going to believe something I shouldn't believe.
But like the only thing here that's like defined in an unreadable manner is the name.
Well,
Or-
and it's a little bit more than that. It's the fact that you've defined concat again, and you've done it correctly.
No. Sorry, I'm talking about 75 to 82.
Yeah, I am too. Yeah, I'm just saying that, like, if you take concat and you inline it, all right. So if you hit the definition I gave it uses concat, you could derive this definition from it carefully, right? If you were careful by inlining and by doing a recursive proof, an inductive proof, you could prove that is equivalent to it. Yeah.
Is it so that the inlining part is the all, not the concat, just for
it's both. No, it's really both. It's the all and the concat. See that your append here, P append Q, that's part lining of concat.
Yeah, but you also have that.
I have it in my definition of
Sorry. You're right. Sorry.
Not
yes.
not in
star.
Yeah.
Yeah, you're right. Sorry. Yes.
But to me, a really important principle is specifications have to be as simple as possible, like you know, with no compromise there, because they're not machine checked.
No, that's
They're
fair.
only people checked, and people are easily fooled.
Yeah.
So anyway, but that's all. I mean, this isn't like enormously complicated.
No. But it's a good one to make the point on. Yeah. Good point. Good point. Yeah, but yeah, that's basically. If we go back to language.v, I think that's everything.
Yes.
Oh yeah, and then just the denotation, but that's nothing. Okay, yeah, we can go back to lean. This is, yeah.
Okay.
This is the part that's comparable at the moment.
Yeah.
Yeah.
Right.
Yeah.
So define the components of the language.
Yeah, but just sorry to nail Colin's point into the coffin here. Yeah, just on line 32, you can see like there he uses the all and the join. And so like we were inlining the plus instead of using the join, and we were inlining the all with having two constructors.
Yeah.
Yeah. Okay. Cool. So next slide, please.
Yes. So that's all of the initial language?
Yeah.
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 We
Now
need to
we
look at the paper.
We need to define nullable and derivative. Online slide. Yeah, that one.
Oh, we can use this. I have them both open here, but
Nice.
we can use this one here.
Yeah.
Oops. Can I copy these?
Let's see.
Whoops, no.
No.
No, I was using, I thought it was an Emacs. I don't know how to apply comments in a block.
Well, I think you're pretty close. Like you can maybe even say, I think you can copy them, paste them again.
Uh-huh. Oh.
And then you can just say diff in front of both lines.
Get rid of the Unicode arrow. Oh,
Why is the Unicode? Is maybe it's just a different Unicode arrow that we need, but
it's happy with those. It's not happy with. Why Why is expected token?
Okay.
That's unfortunate, isn't it?
It's the wrong Unicode token. Like, what is \v?
Actually, this I've copied it from a PDF, so who knows what that is?
Yes.
Yes. So can I just do? Oops.
Yeah, from the source.
There we go. Yeah, it's happy.
Cool. And that's type.
Yeah.
Yeah.
Whoops. No, but I don't. I need.
And we're gonna define
this.
No.
Oh, sorry.
Then colon equal at the end.
Yeah.
And then
Sorry. Can we do that?
yeah, we can do sorry for now. But like, if you look at line 34, right? You see there's like the comment that says nullable, and then
yeah.
It's like it pasted weirdly, but it's the info is there.
Yeah. So what should I have? I should have named this lang.
Yeah, just name them. Yeah, that's good.
This.
Yeah.
And no, sorry, should have called it P.
Well, yeah. Empty.
Oh, but this is a sorry. This is a list.
Yeah.
Yeah, so it's not happy because
Yeah,
oh
yeah.
universe thing.
No, it's not a universe. It's just the empty list always has this problem where it's hard to infer the type on an empty list.
I need to give it this.
Oh yeah,
What should it be though?
Alpha.
No, but it needs to be inferred here, right? I need to apply do the type application on the empty.
Yeah. At P alpha is easier.
Okay.
I think. Like
is alpha abstracted automatically?
No, we're gonna have to add that too.
Oh, okay.
But you're right. But can we just go back to P to lang? I can't remember the. Oh yeah. Okay. Yeah, it is alpha. Great. Okay. So yeah, now we need to add alpha as a implicit parameter.
Mm-hmm.
Yeah.
Okay, that's sad. We need to do that.
Empty list is always a pain.
Yeah. We'll do it again.
Has been in Coq as well, so I assume it's also a pain in Agda. Apparently, it wasn't.
Not so much, no.
Yeah.
Maybe just type in for better.
This one.
Actually, let me see.
Oops. Fun.
Mm-hmm.
I do it like this.
Yeah.
So the cons, list cons, did that.
Better be. Oh yeah, you just need to add a give W type.
Oh yeah.
But yeah, I'm disappointed in that type inference there. That's
just doing something wrong.
I think the reason it was easy for me in Agda was that I made the element type alpha a module parameter. And so it never had to be inferred.
Into that. So that alpha I was expecting maybe I need to give it here. No. Got the same issue as before, which is this implicit lambda.
You can do the fun with another implicit alpha, I guess. In the curlies.
Okay.
Okay. Yeah, now it's two different alphas. Okay, that's fine. That's yeah, like
Maybe
that.
that second alpha should come first because lang is really parameterized by alpha too. I mean, P is slang of
Oh,
alpha.
and you put it here, and then move
Yeah,
this one.
yeah.
Let's see.
No, because if you're returning a language, the language has the implicit alpha as a parameter.
Yeah, that alpha needs to be connected with P.
So yeah, you can say at lang alpha,
Yeah, and then the alpha.
if you want. Like it's worth a shot. Yeah. And the other one as well, why not?
Okay. And then function expected. Term has type.
This is not good type inference. Sorry, but like when we figure
because
this out,
just for doing
like,
something stupid, that's all.
yeah, when we figure this out, we should try to see what we can remove.
Yeah. Yeah, I'm lost here. I don't even know what to do. So function expected at lang. I guess it's how do we pass? Because yeah, we've seen we can do this thing with a function, but it's a type. So how do we pass in the
Yeah, we do want to pass.
argument to a type?
Okay, what happens if we?
Because this is a function, right? So it's just got this implicit argument here, which we're trying
Yes.
to pass in.
Mhm.
So what's
So this is the the definition of lang. Lang itself is a type, so you cannot apply anything to it, right?
Oh, it's not. Yeah, it's not parameterized.
Yes.
Yeah.
Okay.
The type.
So
like,
lang is explicitly saying that it must work for every alpha. So you cannot, apply.
Yes.
if you moved the alpha to the front of the definition of lang, then you start parameterizing lang on the alpha, which would be fine, but also we shouldn't need to.
Just read the error method again. Type mismatch. Yeah, well, it's not.
So can we bring back the alpha in the fun that we have in the body?
Bring back the alpha
Yes,
here.
exactly. Yeah.
Yeah.
Yeah, but
And then we remove the alpha that we have here.
What about that A?
yeah, those are inverters to.
And then this audio, it comes from.
Yeah. This A has this alpha, and this W has this alpha.
So they're
interesting,
but they should be the same.
They should.
So that's why we can't put the alpha there in the fun. We need it.
So it does need to be here, I would expect.
Yep.
I don't know.
Maybe also say alpha is type U just for.
Yeah, sure. Why not?
I mean, okay, this is interesting.
But then this alpha here, maybe it puts like, that's what it's going on about, this implicit lambda business. maybe this alpha gets put here. Maybe I'll try the at, and then it says E.
Yeah.
Expected has type.
So
Do we have this definition in Agda, or?
but this is correct, right? The type checker is right. Alpha is in type U, and lang is in U+1. That's the definition of lang. If we also go up, we can see it, right?
Type U+1.
And
Yes,
alpha,
but this whole thing is the alpha.
Right,
what
but okay, just one comment.
Yeah.
So, Conal said that he made alpha a parameter of the module, right?
Yeah.
So then it is assumed that these two languages work on the same alpha, but this is not reflected on our definition of language.
Right.
Because when we have two languages in our definition, like this A, can you scroll down? So the A on line 35, this is some concrete A, but then you have to return a language that works for any A. So there is no way this is going to type check.
Ah, good point.
Does that mean we need to move this alpha
Yes.
to this side?
Yeah.
Okay, that makes sense.
Yeah.
before the colon, I think.
Oh, yeah, indeed. Very good point.
And I don't know if that's allowed to be. Oh, okay.
Now we're going to have
Yeah.
now it doesn't know what we're talking about.
Why are we not allowed to be implicit now? That's interesting.
Well, because, yeah.
Because
well, we've moved it to the
But
to the type signature from the body to the type signature. So then you need to mention it in the type.
yeah, but it's an implicit.
Go away, yeah. So
Okay.
I need to put this everywhere now?
Oh,
Just an alpha, lang alpha.
Like this?
You don't even have to. Oh yeah, you have to. Oh, interesting. What is the error?
Function expected. So this, I can't do this because this is referring to the I don't know.
I would expect you to be able to do that.
Yeah, this should work. At
Maybe
alpha,
this
without the curlies.
invalid blah. But
Yeah, there we go.
okay.
Yeah, because
Oh,
it's
really?
Well, we can
Yeah.
investigate how to deal with this.
so. But you can make lang just not an implicit parameter. You can make alpha not an implicit parameter since we're not gaining anything from it.
Yeah.
That's true.
And then you can remove the at. Yeah.
Right, and then this thing where you say, well, I can make this at the module scope
Yeah.
a parameter that would help.
Yeah.
Now it's possible we can do that. But
Yeah.
we,
Later.
but we... Join. Can I do
You can
under replace?
Yes.
But can't we just define alpha globally somehow to sort of simulate that
Can't.
module parameter that we have in Agda?
Yeah, but it is also interesting that like this definition of 30, the thing we've discovered by not applying it everywhere is also interesting. Like,
yeah. Also, it points to some interesting generalizations of language operators in which the element type does change within the language.
Yeah, that's true.
Like a mapping function. If you take a language and you think it's a set of strings of characters, right? You map some function from characters to something else. or the other way around, then you can get a language of string lists of something else. That's a reasonable language operator. We just don't happen to use in our language theory work.
Hmm.
Oh, but I would simplify it at first. And,
Oh,
add
failing
parameters
at
later.
the Vim bindings don't work as I expect here.
Okay, so yeah.
I can't do a
This-
find
this
and
is-
replace G.
Yeah, this is where I have some VS Code skills that can work. I only have one skill in VS Code, and this is
Multi-cursor.
yeah, this is where it would have shined.
Oh, great. So now we have this problem.
No, but that's a good, interesting problem. Yeah.
Okay, good.
Oh, see,
So
that's better.
that's simple. Yeah, okay. So this mistake we made last time has caused all this confusion.
Hmm.
Yes.
It's looking better.
Hmm. Then whoa.
So we don't need the at anymore.
Yeah, that's right.
Oh. Light bulb. Thank you,
Hmm.
Jan. This is amazing.
Yeah.
Yeah, no problem.
There's no problem.
There we go.
Okay.
Do we need the at fun now? Yeah, cool.
Good.
That's a relief.
Great.
Cool.
Oh, yeah. I was looking at the wrong thing. Oh, I missed. We got this definition equals over hat. Ah, so maybe we could give some examples now of languages.
Yeah.
Sound like a bad idea.
And actually see if we can
Sure.
let's see the pain of proving without equality.
Okay, yeah.
Yeah.
So what we're saying, we define a language, these constructors, and then we want to prove that B is
In the language.
in the language. Okay. So we do that. So we want char.
Yeah.
Oh, sorry. Oh, hold on. This now is.
I don't even think you need that. I
I
think
don't, we don't need the alpha.
Yes, because
we
it's
don't need the
explicit.
lang.
Oh, I see what you mean. We don't need the lang. Okay.
Yeah.
But what can I write here?
We're gonna
Don't need
write
the
the
equal?
type.
Oh, I was going to define it.
Yeah, just a colon.
Sure.
Yes.
Char.
Yeah. Continue defining it, just like you were.
No,
Make
confused.
character. Single quotes. Yeah.
And then
And can we go back to the PDF? I just need a refresher. Except if you know
we've
what
gone
to do there.
or and B, or char B.
Yeah.
This.
Yeah, exactly. Yeah.
And we went to proof.
And then no. Then you can put that on parens. The or from the or onto the end. and then just the string A or string
yeah.
B?
Assuming this
Yeah.
is a list of chars. A string is a list of chars.
Cool. And then colon equal by.
Yeah.
Let's see.
Yeah.
By
Well, let's just check the.
Oh, good.
So string is not a list of chars.
Okay, great.
It's not Haskell.
They got a more sensible type of string.
Okay.
Okay, no problem.
That is Agda.
Cool.
Okay. By.
By.
Oh, where do I put the by?
There we go. That's it. Perfect. Just a new line after. Yeah, there we go.
Yeah. Like to make sure. Okay, so now we can.
Now we can
Now we're
start.
in our tactic mode. Tactic
But
state.
didn't we want to try without tactics first?
Yeah, let's give it a go.
Yeah. Okay. I think don't use by.
Right. So now we need to.
But how about still using new line? Just crazy
Yeah,
idea.
yeah.
So do you have holes in Lean or?
Good question. I don't know how to sense that. Well, it can tell me what the type of this. This is not very useful.
No.
No,
So I guess the holes you'll see we're in the tactics mode, but not in the term mode.
Okay.
But I don't know that for sure because we haven't spent much time doing writing
this
terms.
This is a useful hole, isn't it?
Oh, because it's of 97 is just A. Yes.
Yeah.
Sorry. You have to. You have to know
Oh.
these numbers are special.
Yeah.
This is
And
A.
we-
This is
we-
B. This is. We know this.
So we
Yeah.
can try with inject left.
Yes. So now the sum. Yeah. Well, I'm going to look at the sum.
Yeah.
Yeah.
I should have put more new lines here.
I think it's
Where is the sum? I can't.
in-
Oh, because it's in Unicode, isn't it?
Yeah.
So it's
I think
in L. Okay.
yeah.
So we want to put in L
And then
You might-
underscore.
underscore.
Yeah, you might need to write sum.nl just.
Yep. And then we want.
So one thing that you can do in Agda
simplicity.
is
Yeah.
you can say, okay, refine this call, and then it would give you a lambda function here. And if we could have that in Lean, it would make things simpler, but I'm not sure if it's possible.
No, we don't. Well, I don't know anything about
Well,
what facilities are available in the term mode.
Okay.
You could start to write the lambda and then add the whole, but yeah.
Yeah, it's more manual work, I guess.
Yeah, you could do that, but
This is increasingly getting less useful.
okay, we have our in L, right? We know
Yeah, so I need to give it a val.
Yeah.
A char, right?
yeah.
Well, I mean,
This.
no, I mean something
I
of
think
the
yeah.
type of char defined in line 20.
Mm.
Oh yeah. Yes.
So just
So now I should be able to give it R REFL.
Okay.
Okay.
Oh,
oh yeah.
Yay. Okay.
Okay, this
Right.
this proof compares with the Agda one at least. Like
Yeah.
Yeah.
okay. Now let's try it with a tactic.
Okay.
Yeah, just copy paste.
Copy
'Cause,
paste.
yeah, you don't have to name it, so you don't have to rename it. So that's
I don't have to name it.
yeah, it's an example. You don't have to name it. Very
Oh
useful.
yes. Yes. Yes.
Yeah. we had these horrible names in Coq for these things.
Yeah.
So just
Okay,
maybe,
so we still have this nonsense of. So sorry, what suggestion?
just sump.
Oh yeah,
Oh
no, didn't do anything.
no, that was
Actually, I've got your faces here, which is covering the tactics.
Oh.
Move your faces down.
I think sim doesn't work because it needs to guess left or right,
I think
and
so
that would
too.
require backtracking.
Tactic that would try both because only one is going to work.
But also the other problem is Simp has no idea about RFL. But
Simp is about
so we have
built-in equality.
We can
so we have to add it to the database. But not that I remember how to do that.
But so if you do like sum.email and then start tactics mode and then you do sim, that doesn't work. So can you, or maybe can you try to apply sim? Sorry, not sim. Sum.enel.
Yeah. And it's wants something of. Whoops.
Yeah, and now try.
No,
No.
don't believe so.
Okay.
That's
Because what we do in Coq is something like constructor
Yeah, I
or
think-
something.
so above the rifle thing. Just
Constructor. Yeah.
Yeah, we'd say constructor in there. But we need our cheat sheet, Walter.
yeah. So above, I
We
have
have
it
a
right
cheat
here,
sheet.
but that's not on the cheat sheet. So
Oh,
above the sump, that the
this one.
You rate,
What,
you
we
rate
write we write something here, don't we?
Yes, go on, sump.
Think.
Yeah. Okay.
Why is this complaining? I'm not doing something right here.
Yeah. Damn it.
What is it? Must have it somewhere.
No. Okay. So
It's not
ignore
in here.
that.
Some way of adding this into the database.
Yeah, I'm working. But you can also just say sump and then space and then add square parens
Yeah.
and then put the constructor in there.
Well,
You might need to say the whole thing, yeah. And then go on to the next, see if we think you
no,
need
it
to
didn't do anything.
Okay.
This did nothing.
Constructor.
Is there a constructor tactic? Yeah, so maybe we could just do that.
Yeah, there we go.
Yeah. All right, so constructor exists. We can add that to the cheat sheet.
Constructor is here. Constructor is
Yeah.
Yes. Okay, still not ideal, but yeah. Can you say riffle just before constructor?
Oh, before constructor.
Yeah, I want to see.
Yeah.
Like, is riffle that smart? No.
No, I don't think so. Well, hold
riffle
on.
is without an E. Yeah, it's without an E.
Of course.
Okay, yeah, it's not that smart. Okay, cool.
Yeah, we just have to add it to the database.
Yeah, we'll figure that out.
We can figure that out.
Cool.
Great.
Yeah, is everyone happy with that session?
Mm-hmm.
Yes.
And I'll stop the stream. Does anyone want to say something before I stop the streams? Don't make the same mistakes last time. All right, I'm gonna stop the stream. Thanks everyone for joining.
Thank you, everyone.